which is being organized by Homi Bhabha National Institute and Indian Society for Electroanalytical Chemistry. And we have today Professor Gunther Wittstock, and I request our President, Professor P.D. Nayak, to introduce the speaker and request him to start the lecture. Professor P.D. Nayak, please.
Good evening to everyone, and I welcome you all for this evening lectures, and thankful to Professor Gunther Wittstock for accepting our invitations to deliver a lecture on electrochemistry. Gunther Wittstock was born in 1965 in Schwerin, Mecklenburg-Vorpommern, Germany. He studied chemistry at University of Leipzig and obtained PhD in electrochemistry with Professor Werner. After stays at the University of Cincinnati, 1992-93, with Professor Hennemann, and at Technical University of Munich, 94-95, with Professor Smith. He prepared his habilitation at the Wilhelm Ostwald Institute of University of Leipzig. In 2001, he became full professor of physical chemistry at Karl von Ossietzky University of Oldenburg, where he learns an electrochemistry group. His research interest is focused on localized interfacial charge transfer reactions, which he studies within a variety of application fields. This includes biomimetic interfaces, nanoparticle assemblies at interfaces, localized electrocatalytic reactions, in particular oxygen reduction reactions in different media. Recently, there has been a particular emphasis on molecular reaction in energy conversion systems. He uses scanning electrochemical microscopy, which is complemented by surface spectroscopies and other microscopic techniques. Among others, his achievements have been recognized by a grant of the Alexander von Humboldt Foundations and Krauss Jürgen Vetter Award of the International Society of Electrochemistry. From 2017 to 2022, he serves as a member of the Executive Committee and Treasurer ISEAC, that is International Society of Electrochemistry. I now request Professor Gunther Wittstock to deliver his talk titled Probing Porous Materials Using Scanning Electrochemical Microscopy. Professor Gunther Wittstock, please, and thank you all.
Yeah, Chairman, ladies and gentlemen, thank you very much for this very kind introduction and the strong attempts to handle all the German words, which is always a challenge and in a very different language. I would like to give you an evening talk today. I'm very happy that we could manage this format over across continents, and it seems to work technically. Hope that this stays on. So my talk will be about probing porous materials by scanning electrochemical microscopy. Of course, the work was not done by myself alone. I would like to highlight the contribution of the co-workers in my group, Bastian Krüger, Julian Lorenz, Mareike Hensch, Luis Balboa Blanca, Alex Ricardo Silva Olaya, and Shoko Ferrasca. I will mention their specific contribution as we go on. And I will also like to highlight the contribution of cooperation partners who in many cases delivered the samples and which we interacted very closely on the different project. This is the German Aerospace Institute for Networked Energy Systems, Huran Türsitz from MP Max Planck Institute in Mülheim, and Frederik Domann, Peter Bieker from the Mead Institute on Battery Technology in Münster, and Jörg Meismüller from Technical University Hamburg-Harburg on Nanoporous Gold. Okay, so you may ask yourself, where's Oldenburg located? So several places were mentioned in Germany. So my hometown, actually, where I grew up, is Schwerin. That's the capital of the local state of Mecklenburg, Pomerania. This is the northeast territory of Germany. I studied in Leipzig, that was here. Then I was in the US. I was in a postdoc in Munich. And now I'm here in Oldenburg. And you see a few places in Oldenburg marked here, which you may or may not know from there. Oldenburg is close to the North Sea, so it has a very moderate climate, not very hot in winter and not very hot in summer and not very cold in winter. It has a port and about 160 inhabitants, growing towards the 170,000 inhabitants. So the campus, the science campus, is located here, and the campus of the humanities is also close by. That's my group in the pre-COVID epoch. Yeah, so and you see it's composed of people from many different countries. And again, the people who made most contributions to that talks are highlighted. Okay, in the talk, I will use frequently a technique which is now not so new anymore, but maybe not familiar to everybody from you. Therefore, I would like to make a very brief introduction. SECM is the abbreviation, and it stands for Scanning Electrochemical Microscopy, and it's a scanning probe technique. The local probe is a microelectrode or ultra microelectrode, which is immersed in an electrolyte solution, and it records a Faraday current. So it's an electrolysis current, and the current flows between that microelectrode and the distant auxiliary electrode. And that also distinguishes this technique from scanning tunneling microscopy, in which a tunneling current is observed, which flows between the microelectrode or the tip of an STM and the tip of an STM and the sample. So here the current loop is close to an external counter electrode or auxiliary electrode, and the current is an electrolysis current, a Faraday current by nature. So that's the main difference. One can use that instrument to record images, but you will see in my talk, it has in my group, the focus has shifted a little bit from recording images towards using that tool as a kinetic tool to make physical chemistry at surfaces, very often without scanning. So we use that very often at a fixed but very defined position and exploit the high mass transfer efficiency at this ultra microelectrode to interrogate surfaces. So now wait. Okay, so here we see a little bit on how that can be done. This is this microelectrode. It makes an electrolysis of a compound that can be oxidized. I typically use in these schematics like generic symbols like R for an oxidizable compound, like the reduced form, and O for the oxidized form of a redox couple. And if we make this electrolysis and the microelectrode is close to an insulating surface, the presence of that surface hinders the mass transport of that reactant to the microelectrode, and the current goes down the closer we come to that insulating surface. And as a quantitative result, you see that plotted here in the blue curve. In this diagram, this shows the normalized current versus the normalized distance. The current is usually normalized to the current which we record far away from any surface. Therefore, it's called ET for tip at infinite distance. And that is a typical microelectrode current. However, if the current is a conducting surface, then we can establish a feedback loop where the mediator is oxidized at the microelectrode and the backward reaction happens at the sample. And now there are two sources for the reactant to the microelectrode. It can come from the sample in this recycling loop, or it can come from the solution. And therefore, the current goes up when we come closer to the surface, because then the recycling loop becomes more and more effective, and you see that as the red curve. In between these two extreme cases, where we have no reaction at the sample or a diffusion-controlled reaction at the sample and at the tip, we have all sorts of cases in between where we have a finite rate constant here, where the mediator is regenerated, but not with infinitely high rate. And then we get curves like this, and then we can make, in principle, two experiments. Either we keep the distance constant and scan our microelectrode laterally over the surface, and then we observe the changes between the different curves at the constant distance, or we pick one curve and approach to the surface and make a kinetic analysis where, by comparing our measured data to simulated data, we can extract a rate constant. That is all fine and well established for smooth surfaces. Unfortunately, many technically relevant surfaces are not smooth. I just put here a few examples from my own work, like a graphite anode in lithium-ion battery is composed of particles held together by a binder. A photoanode in a dye-sensitized solar cell is composed of sintered nanoparticles of titanium dioxide, which are coated by a dye sensitizer. And in this pore space, there's an electrolyte volume. And here's another example on from the area of biochemistry, where enzyme-modified polymer beads are very often used to manipulate proteins and assay procedures. And such a bead mount is also a porous material, and treating that as a smooth surface is not correct, because we have a three-dimensional volume contributing to a conversion. But in that three-dimensional volume, not all of the beads are uniformly accessible, so it's more complicated to reach by mass transport one of these beads which is deeply buried compared to one which is at the surface. And that makes also the evaluation of such data non-trivial. So the first example I would like to bring to you are surface oxides at noble metals, and also transition metal oxides. They are extremely important for electrocatalysis, and we would like to investigate that. There are, of course, procedures already established for that, and one procedure is based on the oxidation or reduction of adsorbates, like adsorbate stripping. One procedure is known as carbon monoxide stripping, or here that is probably more related to the stripping of alkanthiolate layers from noble metal electrodes. So we have a baseline, we put charges in these molecules, they desorb as alkanthiolates, for instance, or in case of CO stripping, we oxidize it to CO2. And then we oxidize or reduce all the molecules, then the current goes back to the baseline. We can integrate the peak, we get the charge, and then we can calculate further with the charge to the amount of molecules contained on the surface, and with knowledge of the area, we get coverages and surface concentrations. However, there's a catch in that procedure, and I would like to highlight that to you. If you have an adsorbate on the surface, that adsorbate decreases the double layer capacity of such an electrode. So if we have a bare electrode, then the double layer capacity, so the background curve would run here. And for a covered electrode, the double layer current or the background current is lower. So now if we come to this peak, we reduce or oxidize our adsorbed species. But when they leave the surface, they also automatically increase the capacity of the electrode. So at that point where the electrode is bare, we have again a high capacity. So now in that peak, we have the charge for the Faraday process, but also the charge which was put into that double layer in all that potential scan from here to here. So at the same time, we get a change in the kind of Faraday charge, but also in the double layer charge. And this is not easy to separate. So one way of doing that is to use the surface interrogation experiments of scanning electrochemical microscopy. So we use a setup which is very similar to what I showed you before, but now we have two microelectrodes. One microelectrode contains our sample. I will explain that in more detail later. And the other one is a microelectrode which we use as a probe, or as it's called here, for interrogation. So that is our tool, and that contains our sample, but they have approximately the same size. And then again, we have a reference electrode and an auxiliary electrode, positioning system, bipotentiostat, and we also use for that an analog switch, which can be programmed. And that analog switch can change the function or can interrupt the connection between the potentiostat and two electrodes. So we can apply a potential, but we can also keep them at open circuit potential so that no charge can flow over the external circuit. You will see in a moment why this is important. So how is this procedure done? We use the normal imaging modes to bring or align the two microelectrodes one over the other. Once we have reached this collinear alignment with a small distance, then we can start to apply a potential program to our sample electrode and to create a defined surface modification. So for a noble metal oxide, it would be a surface oxide. Then at the next step, we disconnect our sample from the external circuit. So now everything what was formed here cannot react by electron moving out to an external circuit. It can only change by reacting with solution components. And in that moment, we start to form a reactant at our interrogator electrode, and that reactant diffuses to the sample and then can chemically react with the adsorbates or the surface oxides. It basically titrates the surface layer. So then as long as we have this oxide layer there, we establish this feedback loop by which the mediator is regenerated. But at one moment, we have consumed all of our layer because it's a finite amount. There's no resupply because there's no connection to the external circuit. And then the feedback loop stops and the current returns to the current which we would expect for hindered diffusion, because then only mediator molecules leaking in from the side of the cell can be oxidized. So then we can make experiments like this. We pose our sample to a certain potential here. Then we make such a titration curve. We integrate, we determine the charge by integration and calculate a little bit further, get the coverage. Then we make the next experiment by which we extend the potential excursion to a higher value. So we form a little bit more oxide, we titrate it, you see the charge under the curve will become larger, and we go on like this, and then we can make relations between coverage and potential. So in order to take up our sample, we use cavity microelectrodes. That's reported already for quite some time. We were not the first ones doing that, but it has turned out in the last years to be extremely successful in my group for various applications. So we start with a gold microelectrode. We etch away the gold in HCl, so we get a recessed electrode. And that recessed electrode, the depths can be measured, and then we can use that basically as a pen or as a pot into which we fill a powdered electrocatalyst. And that could be platinum supported on carbon, it could be nanoporous gold, or as we will see in the second part of my talk, transition metal oxides. Once this cavity is filled, we can record cyclic Tamograms, and you see here the response of those. The red curve shows the cyclic Tamogram of the recessed gold electrode, which is just the empty cavity microelectrode. And then the black curve shows you the response of that electrode when the cavity is filled with nanoporous gold. So since this is nanoporous, has a tremendous surface area, and we get a nice surface voltammogram of the gold. And in comparison to that, the response of the gold electrode, which forms the recessed microelectrode is negligible. So all the response comes from the porous material. Okay, now this is the nanostructure of that nanoporous gold. We can tune the size of these ligaments and the pores by different processes, and now we would like to invest the surface chemistry of that. But there is, of course, an issue in that, because we need to worry about the situation that, of course, the parts which are close to the outer surface of that cavity electrode are more easily accessible to the mediator than parts in the inner filling of that cavity microelectrode. And that is a completely different situation to what I showed you at the beginning, where all the adsorbates or surface oxides are at the outer surface of such an electrode. So we need to answer the question whether this is good or not. I would like to explain you this feedback effect, which is also very important here. This is when we have a microelectrode and the substrate is a large electrode, and we would try to make such a titration experiment. We would titrate this here, but without applying external potential, we would still get an electron transfer to a region which is far away. And since all our solution contains initially only the oxidized form, we form a concentration cell which can drive the back reaction here without titrating the adsorbate. So in that situation, we could not make a titration. We can only make that if the size of that electrode is restricted to that size. On the other hand, such kind of effects that the concentration cell drives a conversion can also be exploited, and we will see in a moment that this is also the case here for the cavity microelectrodes, but in a slightly different way. Okay, the first test, of course, is to make this experiment with cavities of different depths. So we have here a cavity with 11 micrometer depths. We fill it. We go to different potentials, which are listed here. Yeah, so from lower to higher. And the higher we go with the potential, the more surface oxides are there, which we can titrate. If you take a deeper cavity, then we have more material in it. It takes longer until we have titrated everything, because we use a constant concentration of the mediator. But then if we take a 70 micrometer cavity depth, we see, oh, this has a different filling, because that filling is not perfectly reproducible, and we get different charges on that. However, we can determine the active surface area for each filling and then correct for that, and we will see later on that this gives very reproducible results. We would expect that if the depth of the cavity is enlarged, then it would take longer time until particularly the last part of the curve is fully titrated. But this we can't see. We see that once all the material is consumed, the current decays approximately with the same slope here, here, and here. In contrast, to highlight why this is so surprising, we took this electrode, and now we varied the distance between the interrogator electrode and the cavity electrode. So we varied the outer distance. And then you see even a slight change of that distance makes the current to go down, but also to make the slope at the end of the titration to be more drawn out the further away the interrogator electrode is, because that disperses the times for the mediator to reach the sample and titrate. So why is that? So our explanation for that is, if we start the titration, we titrate the outer surface, and then afterwards we can go on with two mechanisms. So the reduced mediator may diffuse in the pore space of the nanoporous gold and titrate the surface oxides directly. But on the other hand, it may also pick up or inject an electron in the gold structures where the gold oxide has been removed. And then the electron is basically transported inside the conductive network. And the oxides are also reduced in deeper layers, more or less at the same time as the reduction happens at the outer surface. Due to this connective network, this surface oxide reduction happens more or less at all the time and does not necessarily require the direct interaction with these molecules. So both mechanisms are probably present at the same time. And that helps to give a uniform response. Okay, so we can then determine the oxide for each of these pulse experiments, divided by the specific charge for a surface oxide on gold to obtain an area obtained in the surface interrogation mode, accessible with a certain mediator and a certain potential. And we can divide that by the electrochemical surface area, which we determine from the reduction of the surface gold oxides in an initial scan. And then we can determine the coverage with the oxides at a given potential. And you see here, these are curves. Each of the symbols refers to one particular electrode. And then this was repeated for each of these experiments. The crosses, the red crosses, are made for an ultra microelectrode, and they are data from literature, so they are not from us. And you see there's a very good agreement at high values, at low values, and here in the middle there's something which we don't yet understand, but which is very reproducible and may have to do with the special structure of these nanoporous gold. So that is a very interesting procedure, and it does not depend on the stripping of an adsorbate like in the situation which I showed you before. Now, if you look more closely to these transients, we can observe something very strange. So initially the current falls off, yeah, that is understandable, but then it goes through a minimum, then rises again, and then falls finally. So why is there a current rise just before the current is falling off? And that is probably due to different kinetics of the reaction of the mediator with the oxide, which we can model. If we assume that we have two layers of oxides and we assume different rate constants for their reduction, then we can simulate curves like this for one. Then the rate constant of the first oxide is larger than that for the second one. And as we consume the second oxide layer, the first layer becomes more accessible, and the rate of that oxide reduction is increasing until everything is consumed, and then the current falls off. The opposite is true if we exchange the rate constants, then we start with a higher current, then falls off to the next plateau, and then finally falls off immediately. And we will see later on that this effect is more pronounced with other materials than for surface gold oxides. And that is a work on, we would like now to go to more interesting catalysts like transition metal oxides, which can be used for alkaline fuel cells and alkaline water electrolysis without using precious metals. Yeah? So when we want to make a transition to sustainable energy, then fuel cells are an important block and electrolyzers. However, this is not possible for the whole world if we rely on platinum, because there's not enough platinum in the world. So doing it with transition metal oxides requires alkaline technology, because they are not they are soluble in acidic electrolytes, and therefore cannot be used in these electrolytes. Okay. So the samples which were investigated here were spinel oxides, here given in that formula. Yeah, that is a more illustrative representation with the valencies given. And this material was brought into a special shape by a hard templating process. That's the work of Harald Thusis. And we obtained that powder, loaded it into the cavity microelectrode, and conducted the subsequent experiments. And in this case, we need to titrate the oxidation states of this cobalt oxide by a mediator which is compatible with alkaline solution. We used the iron tetraethanol amine complex. That is a suggestion from the Barth group for alkaline media. And then again, we titrate the surface, but now we have different oxidation states which this material can assume, and here are some tentative reaction equations given which show these valency changes for different sites of for different copper sites in that spinel oxide. What can we learn from such experiments? Still, the overall amount of charge underneath this curve gives us an idea about the amount of active sites. the magnitude of that current gives us an idea about the rate by which these surface sites react with the mediator in solution, and may therefore have something to do with their catalytic ability. Okay, let's have a look on that. So here you see a cyclic voltammogram of such a spinel oxide electrode. You see different redox signals, and now we made such surface interrogation mode at the indicated potentials. I picked 3 of the curves here and at these potentials. So 1.24 volts, that would be about here, this one on the peak, then 1.39, that would be here, and 1.54, that is after this peak. So if we apply a potential of 1.24 volts, this species is generated, and then if we make a titration, we see a decay, a plateau, and then the final decay. If we go one step further until here, we see already a decay, then something which is going over another step, then a little bit more of that plateau, a decay, maybe even another plateau, and then decay to the baseline. If we go, however, here, then it becomes more interesting. We see a decay to a plateau like this, which is lower than the plateau measured before. Then the current rises to a plateau which is higher, then decays again to the same plateau as it was here, and then there. So we basically see a kinetic spectrum of the different sites which we can address or form at different potentials. And so here this is shown once more, yeah. So a large charge for that, and we can calculate the ratio of these and get about a ratio of 3:1 for the green and the red system, and with respect to the blue, which suggests that we see here the conversion for the cobalt-4 species to the cobalt-3 species, and then furthermore to a mixed valence state where some of the cobalt is in the cobalt-2 state. Now the question is, of course, why do we see different reaction rates? And one assumption is that the mixed valence state has a particular high kinetics for the reaction with the redox mediator, which may also have something to do with the conductivity of that material in that state. But we can do more. We can make a titration experiment, but having a competing reaction. So let's assume the following. We make a potential pulse to generate a particular surface state of this cobalt oxides. Then we allow a delay time in which, for example, water could react with that state to generate oxygen, in an oxygen evolution reaction. And then after a defined time, we titrate the remaining cobalt-3 or cobalt-4 species. And then we can again calculate the charge, but now as a function of this delay time. And you see such an experiment here. So the charge was determined as a function of the delay time. And then we see that we have a very rapid decay within the first 2 seconds. That is the cobalt-4 species react away. And then we have a much slower conversion in the remaining 30 seconds. That can be, of course, analyzed in more detail here as a function of the potential to which the potential excursion was made to generate the cobalt oxides. And then you see if we have only the 1.34 volt and it's only cobalt-3, then we have mainly this decay. If we go to higher potential, we have this initial fast decay there before. That can be fitted. We can extract rate constants for the different sites on the cobalt atoms at the surface of that complex oxide. Okay, so here again, plotted in a logarithmic scale, and then, okay, that's there. If we would like to build an electrode with these transition metal oxides, there is a major challenge is to process these materials to an electrode, because they need to be connected with binders. Very often conductive additives must be added. And if the electrode loses its activity or other functionalities, then we start to make a new electrode with all the composite preparations, which can be very involved. and usually also do not really allow a regeneration of an electrode once the composite is coated. And therefore, we have an idea for quite a long time already to rethink the work with these porous electrodes completely. And instead of using a solid electrode, to use a liquid-liquid interface as a particle support. That work is mainly driven by Shoko Feraska, who came to my group as a fellow of the Alexander von Humboldt Foundation. There's a number of papers. I would like to give you just a short idea of that concept. So if we look at working systems who do photoconversion in nature, we find that these are usually membranes, biological membranes, and a technical system which could mimic that are either biomimetic membranes or liquid-liquid interfaces. Such liquid-liquid interfaces can be formed between two electrolyte solutions which are immiscible, like an oil-water interface. And the requirements are that the two solvents are not miscible. There should be a density difference between the two liquids so that they form a stratified layer, and both should have a dielectric permittivity. In particular, that's an issue for the organic solvent. Yeah, and then here you see like the charge separation in a schematic way for the natural photosynthesis, and here for a set scheme in light harvesting. So there's an interesting question if we think about that. Yeah? So I compared here two integrated systems where functions are highly integrated. There is a man-made system where I took a cross-section of a semiconductor chip and a schematic representation of a plant cell. And there are a few common features like a hierarchical structure, addressability, transport processes, signal processing, bridging nano and microscale, and horizontal and vertical structuring. This occurs in both of these systems, but then there are also differences. A semiconductor chip is solid, state, harsh process condition. It offers high switching rate, and the transport is mainly made by electrons and holes. In the biological system, the compounds are soft. They are made by self-assembly. They are able to self-regenerate. They are able to exploit molecular recognition, and they are formed at ambient temperature. Usually there's a low switching rate, but and that is due to the transport, which is made by ions and molecules, not by the much lighter electrons and holes. But if we compare the lifetime of that, then we come to very interesting conclusions. This looks like much more rigid stuff, stable. But if you look around, in my environment, there are trees which are now over 150 years old. In our climate zone, they exchange the leaves every fall. The leaves gone. Every fall, every spring, the leaves come again. And every photosystem lives only for a few seconds, and after that, it's renewed. But the overall system, the tree, lives for over 100 years. So I don't know any semiconductor chip who has lived for 150 years. Okay, so that is interesting. So now when we want to exploit that, we need to arrange semiconducting oxide particles at an interface between such layers, and we need to do that. We use hyperbranched, or most of the experiments are made with hyperbranched bismuth vanadate particles. They look like this. And then we can exploit photoelectrochemistry at these layers. We detect the products with a microelectrode over such layers, or we use mediators and then manipulate the system by switching light on and off. I would like to explain you this stepwise a little bit more in detail with a few examples. How do we get the nanoparticles to the interface? And actually, this sounds difficult at the beginning, but then turns out to be very easy. So we start with an aqueous phase, which contains a salt like perchlorate. And then we add the organic phase. In this case, the organic phase is lighter, and it also contains a perchlorate salt. So now we have the perchlorate as a common ion, and that will partition between the two solutions. So usually some of the perchlorate go from the organic phase spontaneously to the aqueous phase. They take their charge with them and charge up the aqueous phase negatively, and the organic phase will be positive. that generates the potential difference between the two phases, which can be calculated by the Nernst-Donen equation. Yeah, and there's the ratio between these ions in the two phases are important. By manipulating the ion composition, we can vary the voltage, similar to applying a voltage over a potentiostat. Okay, now if we have in the aqueous phase, in addition to our salt, negatively charged nanoparticles, they don't like when the aqueous phase is charged up negatively and spontaneously go to the limits of that phase. And that means also to the interface. You have here a photograph, yeah, after 2 minutes after putting the organic solvent on it, and after 10 minutes, you see there's a layer of nanoparticles spontaneously arranged at the interface. If we would like to renew that nanoparticles, we shake the solution, let it settle, and we have a new set or a new selection of nanoparticles at the interface. So we form a defect-free interface down to the molecular level with self-healing, and it's also renewable. We can regenerate the catalyst in this way, also exchange it. We can use physical separation, which is very established in chemical industry, to handle different solvents. And we can control the interface polarization by the composition of the solution or by an externally applied voltage. Okay, this looks like this. And as a system, so this is the interface is actually reduced to a very small size in a capillary in order to align it collinearly with a microelectrode with the help of a microscope. And then we can make all the experiments which we did before at solid electrodes, we can now do at this liquid-liquid interface. So here we see approach curves which were fitted, which have different kinetics for the regeneration of the mediator, which takes up a photo-generated electron. And the rate depends on the polarization which we induce by different compositions of the electrolyte. Yeah? In a very systematic way, we can construct something like Tafel plots for that weight constant. And again, we can make these pulsed experiments where we illuminate this nanoparticles, wait a time, and then interrogate what has happened. And these particles can make oxygen evolution. The intermediate is an adsorbed hydroxyl radical, and two of them can combine to form hydrogen peroxide, so or can be desorbed. So we allow that reaction to proceed, and then we titrate the remaining hydroxyl radicals. And again, we see that independence of the waiting time, we see a decrease on the surface concentration of the intermediates. We can fit that to a rate law and extract rate constants from that. Again, that's a very interesting and also very new concept for the reaction, but also a method to address those surface properties. I think I would like to bring you one more example, and that is surprising clean surface electrochemistry of nanoporous gold, which we also investigated with this cavity microelectrodes. So nanoporous gold is a material which is obtained by dealloying a silver-rich gold-silver alloy. Silver and gold form solid solutions, so they are miscible in any ratio. And we get a network of ligaments which does not need any supporting material. It's bicontinuous, so there's a continuous metal phase and a continuous solution phase with small feature size and a high surface to volume ratio. It can be surface modified, has catalytic activity, and is a rather versatile material, which we use to study systematically structured property relationship. And that is done not only in my group, but also in a research group funded by DFG. I'm the spokesperson of that, where we investigate also similarities and differences between gas phase catalysis, liquid phase catalysis, and electrocatalysis at those materials. So when we started, that was our result. So we had a flat gold electrode. We tried to do metal under potential deposition, and we also tried to do that at the nanoporous gold. And after half a year of work, this is what we achieved, and it was really disappointing. So that was not really very encouraging. So then we went on and step by step learned the different tricks. And then I make a big jump and now we are at the current state. So we make this is the work done in Hamburg. So we make a master alloy. We have this ingot. We de-alloy the ingot after very careful selection of the procedure. Then we receive that material. We kind of mechanically destroy it and make a powder. And that powder is filled into a cavity microelectrode. It's now located at the end of such a cavity microelectrode. And we can make cyclic Tamograms with it. And you see here the very nice cyclic Tamograms of these layers, and with very high resolution. And then we observe very interesting changes. So in the upper branch, you see cyclic Tamograms, which we record in sulfuric acid, and in the lower one, which we record in potassium hydroxide solution. So if we make the first scan, the picture or the appearance of the surface gold oxide completely changed. This big peak is lost, and instead these smaller peaks develop, which corresponds to single facets of the gold crystal. And after even more cycles, that remains like it is. However, if we do the same thing in an alkaline solution, the shape of the voltamogram stays the same for over 100 cycles. There are only minor changes. However, if we then transfer this sample, which was cycled 100 times, to sulfuric acid, then we immediately get the same response as we had here. We have this big peak, and then the second scan, this is gone and looks like this. Yeah, if we continue in potassium hydroxide, of course, it stays the same. If we then transfer this sample, which was pre-cycled in sulfuric acid, to potassium hydroxide solution, then we get something which looks completely different than what we get if we go immediately to potassium hydroxide and we see this peak is gone. So in combination with XPS analysis, we attribute that peak to silver species, which is on the surface of that and is removed in the first exposure in sulfuric acid to positive potentials, but it can stay there in alkaline solution. So the process which we think is like this. So we form an oxide, then silver is dissolved, and surface oxide pulls the silver atoms to the surface, and step by step we basically deplete the surface in silver. And there's quite a mobility of the atoms. If we do that in an alkaline solution, we just cycle the silver and form a silver oxide layer, which is then reduced, but the silver stays on the surface. And that has a very important effect because the silver stabilizes these high energy defects at the surface, whereas if the silver is removed, then the first surface starts to restructure and forms larger terraces of low index single crystal planes. So that is also seen in XPS here. So if we cycle in sulfuric acid, the surface concentration of silver goes down. That's the one of the starting material, and that is after cycling in alkaline solution, which pulls more silver to the surface. But that's not all. We can now start to make the UPD experiments at these surfaces. And after playing around with the concentration of this lead, which we use for these UPD experiments, we can specifically and selectively decorate only certain facets of that. So if we have very low amount of lead, we can only decorate this peak. If we add more, we fill the next, energetically next favorable places. If we make more, the next one. So we can step by step fill the surface with lead species. On the other hand, the lead species also stay on the surface if we go to positive potential. So then they form plumbite species or even PbO2. And so we can cycle this again and again and get a stable coverage, which depends on the volume concentration of lead species. Now, this phenomena can now be used to selectively take out certain sites of the nanoporous gold surface and then see which effect has this on electrocatalysis. So here's again the process which is there. So this is the UPD process at the beginning, and this is the UPD process after cycling in sulfuric acid. And this is the model which we have for that. If we have a fresh surface, then we have many high energy surface sites and a little bit disordered surface and a silver content. After cycling in sulfuric acid, we remove the silver content, which is still there, and we form larger terraces of low index crystal facets in that material without really largely changing the overall size of these ligaments of pores. And that is in agreement with these change of the UPD signals from these broad signals to very specific signals, which we obtain in the pre-cycled material. And that's then the result for the methanol oxidation. So here for different concentration of remaining silver. So the initial material is this one, 30% surface atoms is silver. And after cycling in sulfuric acid, it's less than 1%. So with the silver, we see an earlier onset of the oxidation of methanol. So that's the oxidation of methanol. However, a lower current at the top. And then here, a few other situations here, also an earlier onset of probably carbonate formation, and then also a shift in the potential for the surface gold oxide reduction. If the surface is depleted from silver, then we see higher currents here, however, a later onset here. If we translate that for these two regions to Tafel slopes, we get these two regions, and then we see, okay, with silver, the initial current is higher, but the slope, I mean, the increase of current with potential is for the clean gold surface larger. And in this region, there's basically not too much of a difference. So we conclude it's essentially still the same mechanism. Just the initial step, the rate determining step, is accelerated by the presence of silver at that potential region. Okay, so this can be now done in a similar way for more different concentrations of lead, where we poison essentially certain surface sites with lead and look for the effect on the methanol oxidation here. So again, we see here the signals for the methanol oxidation and here the signals for the UPD. And here in the insets, you have a few regions of this voltammogram enlarged. So this one belongs to this region. And here, this is the Tafel slope made over that area. So again, we see as we increase the lead concentration, the current drops because more and more sites are occupied. However, we see that the peak currents do not drop, and initially they even increase. For small concentrations of lead, they even increase. Then number 4 is here. That's this one here, and then strongly drop. And if we now look, which are the areas which are occupied here, when the current drops so sharply from here to here, then we see, these are the 111 and 110 surfaces on that area which are dropped. So we see, and that was a little bit a surprise to us, that the high energy surface sites on that material, where we have defects in the 100 layer mainly, that they are not really important for the electrocatalysis. These are more the terraces for the 111. If they are occupied, then the current drops enormously, and therefore they make the major impression on that. Here is just, again, a pictorial representation, which is not the correct surface structure, but the idea of that experiment, that we selectively decorate by changing the amount of UPD lead certain surface sites and then explore what the remaining sites do for the methanol oxidation. Okay, so the conclusion for that is, so the onset potential shifts to higher value with increasing lead coverage, partial coverage of lead with small coverages, but only with small coverages, promotes the reaction. The exchange current density decreases, but that decrease maybe looks small, but it's a logarithmic scale. And the Tafel slopes are similar. Yeah? So we assume the same step is the rate determining step. And this is similar to the trends which we observe for residual silver. And if lead covers these low index facets, then the methanol rate drops dramatically. Yeah? So that's then this change from here to here. Okay, so I asked the chairman, should I continue or should I stop here? I have 2 sections more.
Continue, sir. Continue, sir.
Yeah, I should continue. Okay.
Yes,
I brought you something which is a little bit different story, but has a similar overall theme. And this is work which we did on lithium oxygen battery. And this has 2 parts. One is the oxygen reduction reaction in organic media in context of these batteries. And the other one is the change of morphology, again, has something to do with morphology and reactivity of lithium metal electrodes under cycling condition. And then at the end is kind of as the highlight is really some imaging with the SECM. Okay, the lithium air battery consists of a lithium metal electrode and a porous electrode, which is a gas diffusion electrode to make oxygen reduction. And then the lithium ions go here to form a lithium peroxide. And then in the charging reaction, they would go back. That seems to be like a very ideal system for energy storage because we have a lightweight metal and also a very lightweight high potential oxidizer. However, there are very large challenges to bring that into a safe technical system. We need to have a stable interface at the lithium metal electrode. Dendrite-free lithium deposition is a challenge. Stability of the electrolyte must be ensured both with respect to the very reducing lithium, but also to the very oxidizing oxygen and reactive oxygen species. And that could be maybe done by the identification of host materials for lithium like silicon and other tin alloys and things like that. So let's first turn to the gas diffusion electrode. So I have sketched here a process to make such gas diffusion electrode, which was actually done in Fraunhofer Institute in Oldenburg. And it's based on a carbon paper, which is then coated with a catalyst layer and heated and dried. So, and then the question is, what species do we form if we make the oxygen reduction in such an organic electrolyte? So we did it in DMSO, and we suspected from bulk experiment that not only the peroxide is formed, but also the superoxide. And in order to find the superoxide, we added a fluorogenic dye. And that fluorogenic dye would react with the superoxide, but not with the peroxide, and form a fluorescent molecule. And that fluorescent molecule can be observed. So what I have here now, and I think I need to check back. Oh, here. You can see the time evolution of that optical signal. I think it's 40 seconds, so it's a little bit accelerated compared to real time. And you see the strong development of that fluorescent molecule. If we make a control experiment here, then after 40 seconds, we see nothing. Yeah, the control experiment is done in the absence of oxygen. So you see first that a lot of this is formed, that the formation is inhomogeneous over that electrode. And so there are lots of things which are going on beside the reaction, which is just written down for the textbook. So here once more. So now how can we investigate this now? So we constructed a special measurement head for the SECM. You still see here the microelectrode. The sample is sandwiched here between O-rings. But now we have built around that system 2 gas reservoirs, an upper gas chamber and a lower gas chamber. They can be supplied with different gas mixtures, and the idea is to provide oxygen here and to remove oxygen here. The sample is then put in here with a special combination of PDMS and silver tarnish for connecting. I don't want to go to this technical details, but at the end, an oxygen partial pressure from here will cause a diffusion through the gas diffusion membrane into the atmosphere, which is argon above the sample and then carried away with that. So we would have constantly a passive permeation of oxygen into that cell. So we start by filling both chambers with argon. Then we inject our electrolyte solution into that argon atmosphere. Then we start again, and now we make the upper chamber to be started with argon and the lower chamber with an argon-oxygen mixture. So then, okay, now we should detect the permeation of oxygen through that membrane, and we did that. And initially we started with tetrabutyl ammonium perchlorate in DMSO, and everything worked nice. Yeah? So we get a nice current for the oxygen reduction at the microelectrode, depending on the permeation rate of oxygen. The same experiment made in lithium perchlorate, we couldn't get a stable current. The current always decayed and was going like this. So I remembered my old history in analytical chemistry, and there's a process which is called pulsed amperometric detection. So I said, okay, let's do that. So after a reduction pulse with the microelectrode, we clean the microelectrode by an oxidative pulse, removing whatever was maybe deposited on the microelectrode, because this looks to me like deposition or passivation of the microelectrode. And then when this is clean, we start again a reductive pulse, and then we clean again. Measure, clean, measure, clean. And then we get these transients. The last point of these transients is taken, and if we connect that, we get the perfect line in the electrolyte, which was anyway good. But also in the lithium perchlorate, that recipe works. We take the last point, and then we get a stable recording for the oxygen permeation into that solution. The price we have to pay for that is, of course, a longer measurement time, because we always need the cleaning pulse and the measurement pulse instead of just measuring one value. So here you see now another experiment where we not only pulse the microelectrode to detect the influx of oxygen, but at certain time we also pulse the gas diffusion electrode to start the oxygen reduction at the gas diffusion electrode. And if this happens, we don't expect oxygen to come to the microelectrode. And this is what we see indeed. At the moment when we start the oxygen reduction at the gas diffusion electrode, the oxygen influx in the solution stops, the current decays, and if we let the gas diffusion electrode again be at open circuit potential, then the oxygen reduction current at the microelectrode is slowly recovered. If we make again a reduction pulse at the gas diffusion electrode, the current again breaks in. So that is all what we expect. This is not too surprising. However, we then also looked at the cleaning pulses, and there was something which was very strange. At the moment when less oxygen entered the cell because the gas diffusion electrode made the oxygen reduction by itself, we see that we get higher currents for the cleaning pulses. And it should not be the case. At least my naive initial understanding was that this should not be the case. So why do we have more to clean from our microelectrode if less oxygen enters the cell? And the problem is, again, that we may not have just the formation of peroxide, which is kind of the standard reaction, but that if a substantial part of our oxygen actually forms superoxide or lithium superoxide, which has a certain solubility in the electrolyte and diffuses to the microelectrode. It's then passively collected at the microelectrode, forms a deposit on the microelectrode, and is then in the cleaning pulse stripped off. Okay, if this is the case, we can provoke that experiment even more clearly, and that is done here. So we make oxygen reduction at the gas diffusion electrode, hold the microelectrode at open circuit potential, and passively collect the peroxide. After that, we make a stripping experiment, and you see here the result. We do the whole procedure, but have only argon in the cell, no oxygen in the lower gas compartment, and you see there is still a little bit of a trace, which is probably still traces of oxygen coming in. If we have, however, oxygen in the lower compartment, and the gas diffusion electrode can really make oxygen reduction here, and then we make after a waiting time, so we make this for 120 seconds, and then wait 15 minutes to give enough time for the microelectrode to collect. And if we then do this experiment, we get a huge stripping peak for lithium peroxide. If we then take the charge and calculate, we come to about a monolayer. So we clearly see that during the operation of such a gas diffusion electrode, these reactive oxygen species are released into the solution, And that has, of course, consequences for the requirements towards stability of electrolytes and other passive components in that system. Okay, so I would like to conclude with a newer investigation which my student made. So when we are interested in battery interfaces, we work on that already for some years. And what we usually did was post-mortem investigation. So the battery was challenged in a cycling machine, and then we put it into a glove box. We opened it, recovered the electrodes, and imaged their reactivity or their state. And opening these batteries, recovering the electrodes, even a rinsing procedure may already change the surface state of them. So that was not really an in situ technique because it was only always post-mortem and we could not look on how the electrode would further behave. And that problem bothered us a lot. So now we had a new project where lithium electrodes were again in the focus. And then this is a survey which shows you the advantages and disadvantages of lithium metal electrodes. So high energy density, but low reversibility. And this is due to this tendency to form high surface area lithium, like lithium dendrites, and also then the stripping. So we would like to understand that and maybe devise additives or procedures which mitigate that effect. So in that studies, we use the feedback mode. We add a mediator in organic solvents under glove box condition. This molecule has turned out to be extremely stable and extremely good for that purpose. So much better than other mediators. So we prefer that a lot. So then we have here a graphite electrode, or in our case, a lithium metal electrode, which forms a solid electrolyte interface. And then we probe the passivating property of the solid electrolyte interface for electron transfer reactions, because this is very negative and they can pick up electrons. So if this layer prevents electron transfer, we should get negative feedback. If this is broken, we should get positive feedback. But at the same time, lithium intercalation should be possible. So now we want to do that while current is flowing, while we charge and discharge the electrode. So first, we calculated a little bit what would be a realistic current density for such a lithium metal electrode if it would be operated against an NMC cathode. That is shown here. We know that the surface of these lithium metal electrodes is treated by the manufacturer with a layer which makes them non-adhesive. This contains fluorine, as one can see from XPS. And then we constructed that measurement cell. So this is a cross-section of the SECM cell. The microelectrode is here. Our lithium metal sample is here. There's a special way of contacting it from the bottom, but that's not the main point. The main point is this here. This is a combined auxiliary electrode for the microelectrode, but also a counter electrode to charge and discharge this metal electrode. And in order to do that, we have a potentiostat, and that potentiostat can switch the role of the working electrode between the microelectrode and between the lithium metal electrode. And then it can be either operated in a 3-electrode cell with the microelectrode, the auxiliary electrode, and the reference electrode, or in a 2-electrode setup between this lithium metal electrode as a working electrode and the counter electrode as a second electrode. So we then have to remove the sample, and we have to the microelectrode, and we have to worry if we make the working distance very close, then it might be that we shield the reactions underneath the working electrode. So we made computer simulation with COMSOL to explore that effect. So if we have 2 parallel lithium sheets, we have homogeneous current density distribution for different concentrations of electrolyte, just an edge effect. If we have an opening here, which we need to insert the microelectrode, we see a small variation here, but it's still a tolerable change in the current density distribution. But if we have our microelectrode at the working distance, then we see a strong drop of the current density if the microelectrode is close to the sample of interest when we do the charging discharging routines. So what we have to do is we have to intermittently retract the electrode, make the charging discharging, engage the electrode again and continue. But that can be done with rather good reproducibility. So when we do that, now we have a cell where we can really record reasonable charging discharging curves for a lithium electrode. We could reduce the overpotentials by a factor of 40 in that SECM cell. So we can now really follow the lifetime of such a lithium electrode in that cell. And then we could record images in between. So we have an image. We usually record a forward image and a reverse image also as a control measure. And then we challenge the lithium metal electrode with charging, discharging cycles of increasing number and increasing current density. So you see, we started with 0.35 milliamps per square centimeter, not too much happened. Then we increased the cycle numbers. Then we had we made it for longer time to pass more charge, then for even longer time, and then we increased the current density. And then you see, okay, the surface is not changing too much. And then if we go to too high charges, then we slowly start to see changes. These curves are some kind difficult to evaluate because both the distance and the reactivity may change. So we used to plot them in histograms, the normalized current for each image. Yeah, so this corresponds to one image, and then we make a histogram of normalized current. We measure this current at far distance during that series of imaging, always just before the image, because we also have a small decay of the current during such a long experiment. To cover or to deal with that, we make the normalized current. So we see that the normalized current distribution gets broader as the experiment proceeds. So we get more variation of reaction rate over the surface. And it also gets lower because we probably form a solid electrolyte interface of higher thickness. That's the first observation. The second observation can be seen when we go to higher current densities, which are too high. Then we see that the surface really changes and a new area pops up with high currents. So we then concentrated on that. So here you see it again. Yeah. So initially not too much change, then a little bit more change. And finally, we form isolated regions with very high current density. So if we then want to investigate those ones closer, we can position the electrode over an area far away from such a spot and directly on top. Then we make an approach curve and we stop the approach curve. And we see, first of all, a height difference, which tells us that something like a high surface area lithium was formed because there is a different point at which we have to stop the current. And secondly, if we compare the approach curve, then we see that the current steeply rises to much higher values than in the case of the original surface. Yeah. So we see that not only the height was changed of that, but also the reactivity is changed. So that means this high surface area lithium, which is deposited in such procedures, is not only rising up the original surface, but it also has a higher reactivity, or the solid electrolyte interface formed on such structures is less, does not prevent electron transfer reaction as well as the layer on the normal lithium electrode. Okay, so as conclusion, so the surface titration mode, which I introduced initially, can give quantitative and kinetic information about reaction sites. And I tried to connect it with some questions which are still there as open question. Yeah? I mean, the open question, of course, is how can we get into observation about chemical nature of these sites and the effect of mediators, in particular for the small amount of material which we have in such a cavity microelectrode. We can effectively polarize oxide particles, semiconducting oxide particles at liquid-liquid interfaces by different means, and can use that similar to other electrodes with all the advantages of regenerating surfaces. But the question is then, of course, how can we combine that to an integrated system involving mediators, solvents, and so on? So we need new technologies to work with these liquid technologies. For the nanoporous metals, this is very interesting to study the electrocatalysis by voltammetry with the cavity microelectrode. that brought us an enormous step forward in understanding the details of the surface chemistry, because the quality of these CVs is almost close to that of single crystals. However, again, the question is about structural information from these low amount of materials, which would be extremely helpful to gain, particularly also in an in situ situation. Oxygen reduction reaction in organic electrolytes in the presence of lithium plus leads to lithium peroxide, but also to other soluble species. And the question is whether solvent mixtures, mediators, or other additives can drive the product spectrum of that reaction to maybe form less of these soluble products and direct the deposition reaction to a certain way. We're working on that now. And lithium metal forms dendrites, and they behave very different than commercially pure lithium metal surfaces. Yeah? So again, removal and modification of these surface layers, electrolyte additives, and charging pulses for optimizing the behavior of lithium dissolution and deposition are, of course, means to do. And that is also interesting to look at that with an SECM and to handle the challenge of deciphering reactivity changes, form changes, and topography. This is what I wanted to bring to you. I thank you very much for the attention. And I would like to connect that with a greeting from my student, especially from my Indian PhD students, which they made for you. So I think they are all very sorry about the cricket games which had to be cancelled. So they invite you to join the Euro 2020 meanwhile. So thank you very much.
Thank you, Professor. The talk is open for discussion.
Yeah, any audience, they are having any question? I'm sure Professor will be happy to respond.
Yes, of course.
Yeah. Even a student can ask question. Yeah. Or you can put your question on chat box quickly. I'm sorry we didn't declare that before. Probably meanwhile, Professor, can I just ask something to you?
Yes, please go forward.
Yeah. Definitely the interesting point, I mean, entire talk was very much interesting, but this liquid-liquid interface, I mean, what is the typical dimension of your electrodes there when you use them? And
okay, yeah, I think the pipettes can be drawn out to very small dimensions. I think probably our ones are in the range of 10 to 20 micrometers, 5 micrometers, and the microelectrode is typically 25 if there's not another special requirement. That is to stabilize this interface mechanically and to to also record a defined electrochemistry at their surface. So we started doing it at macroscopic interfaces, but then it's also much more difficult to make the approach. That is much easier with the pipette because we can observe them with a microscope and determine very precisely the distance towards the microelectrode. That is the main advantage of using that in the pipette configuration. For a device, of course, one would like to have macroscopic surfaces, maybe even emulsions.
Now, in that pipette kind of electrode, do you find, I mean, is there any possibility of accumulation of nanoparticles suspended in the solution to be accumulated the smaller part of the pipette than the bigger part of the pipette? So you blown it to a
here, yeah.
okay, yeah.
This one, yeah. Well, I think it's
more accumulation, yeah.
Yeah, but I think the particles stay in, they don't enter into the organic phase. So in this case, I think the aqueous phase is inside. So we get a rather clean surface. This is not,
Okay.
yeah. I think that's, and the material which is in the back doesn't play in that game. Yeah. So here you have material that's a reservoir, but it doesn't plane, and we can just refill it and generate a new surface.
Okay. Okay.
Yeah.
Yeah. Some more questions were written on the screen. And I mean, one, Daisy Mehta. I mean, I will read the question, Professor.
Yeah.
Somebody has asked, what is the mixed
What is
feedback mode you meant for? Yeah, you can see that
mixed?
question, Professor.
Yeah, I see the question. Did I say mixed feedback mode?
Yeah.
I'm not sure if maybe you can. That can be explained a little bit more in which context this was used, or I'm not sure what that means.
You may go to next question in that case.
Yeah, maybe I go to the next one, and that says in the first part of your lecture how to put the metal oxides in the ultra microelectrode. Yes, the cavity microelectrodes we fill by having the powder, let's say on a mortar, and then we just gently dip in the cavity microelectrode and press a little bit. So it's just filled by knocking into the powder. It's actually very easy. And then we also remove it by exposing it to an ultrasonic bath in ethanol or something, and then the particles fall out again. That's actually has not turned out to be so difficult. And then Krishnamurti asks whether does the shape of the electrode impact the adsorbate subsequent chemical oxidation electron injection? To which part does it refer? Shape.
Maybe Professor take on the another question.
Yeah, oxygen reduction in lithium-ion battery. What kind of solvent mixtures are these, purely organic or even other solvents to be considered? Okay, so what I showed you here was the oxygen reduction reaction so far. That was DMSO. At the moment, and I haven't included results in that paper, we work on mixtures between organic solvents and ionic liquids. The rationale for using ionic liquids is that they of course have a low vapor pressure, which is good for a gas diffusion electrode open to a gas atmosphere. But the first results show that the chemical reaction with such a mediator, which is also needed for recharging them, they are much lower than in conventional organic electrolyte solutions. So the evaporation problem is solved, but the kinetic problem is much more severe. So that story is not yet at an end, I would say. So then
you can take on that. Sai Kumar J. Naidu.
Any
point?
wide study carried out on stability of porous material at different conditions? Yeah, I mean, we did it not on a broad scale. We worked with Nanoporous Gold, and we did that intensively. And there were contradictory reports in the literature on the use of such materials and sensors and so on. Some reporting coarsening, and other did not reporting coarsening. First of all, there's a big role of the electrolyte. I think I made that clear in my presentation. If we go to alkaline electrolytes, we keep the residual silver at the surface, and that stabilizes the high energetic places on the surface, and that is actually quite stable. Another way of stabilizing that is also to start with a ternary alloy and then dissolve a less noble element, but then, for example, having some platinum in it, and then that platinum atom do not dissolve and stabilize like the silver and alkaline solution, also the structure, also an acidic solution. So that's another way. But again, it requires platinum or something like that. But otherwise, in an acidic solution, these surface atoms are very mobile and change places all the time. So this is what we find. And we have now even more evidences that even storage overnight brings again the silver to the surface and so on. So there is a lot. These electrodes are more mobile than we think, like from a conventional idea. Now, does the shape of the electrode impact adsorbate and subsequent oxidation chemical injection in the cavity microelectrode? Okay, we have worked with gold disc electrodes and produced cavities of different depth. And it seems that we see the same tamograms regardless of the depths. So there's a very well conducting network of the nanoporous gold, and we don't see any effect of that. We usually characterize that and normalize it either to a current which we get from capacitive current or by a surface gold reduction peak. Again, for that we get very reproducible data, and that doesn't seem to be a problem. What is not reproducible is the filling status of the cavity. So if we do that by dipping the electrodes in the powder, we take up different amounts of nanoporous gold each time. So we need to normalize to some measure of surface area, which we get from the electrochemistry. We cannot say we have a cavity of 10 micrometer, therefore we have this and this amount of material. We need to measure it for each individual filling. But the shape of the cyclic tamograms with a deeper filling or deeper cavity or a more shallow cavity, there's no difference. Does it answer the question?
Yeah, I think so.
Okay.
Because
so then, do we have I answered all the questions now from the chat? Oh, now
you
there's
responded.
There's now one popping up on my screen. How is this going on? So this is strange. So on my presentation screen, there was a short pop-up. Which mode have you used in your studies, and which is the significance of combining? And redox competition mode. No, I try to avoid, when this is meant with combined mode, I try to avoid combining different modes, because then I don't have a guideline in treating the data. So in the first part of my talk, and I can go back here, I used the surface interrogation mode, which is an own mode of SECM, this one. Yeah, you could, and this is similar to the feedback mode. So the similarity comes from that. Our solution is filled with the oxidized form. Then we first make a reaction at the microelectrode, and the product of that reacts at the sample. So it's not substrate generation tip collection, it's feedback mode. But the feedback can only be sustained for a short time, and then the current goes back, and then only the reaction happens here. So we start from positive feedback to negative feedback in one experiment at one and the same location. So this is called surface interrogation. It's also not redox competition mode. Oh, sorry, there was, yeah, is it possible? Okay. So this is surface interrogation mode with the liquid-liquid interfaces. We used substrate generation and substrate generation tip collection mode, where the substrate is the capillary or the interface with the nanoparticles. We also use the feedback mode with cobalt mediators. And we have unpublished results about the redox competition mode, but I haven't talked about that today. So I think my talk did not contain anything about redox competition mode and also not about tip generation substrate collection. So does it answer the question? Generally, I would try to avoid mixing modes because then I don't have a tool for evaluating the data. Then I get some pictures or some responses, but I cannot extract anything from it. Sometimes it's difficult to avoid that mixing, yeah, but it's usually not desirable. Okay, there was another question from Milan Day. Is it possible to study conducting ionic passivate layer battery materials by SECM? So you mean ion conducting materials which are passivating for electron transfer. This is what we do, yes. That is possible to do. And the solid electrolyte interface is an ion conducting phase, which should have insulating properties for electron transfer. And we study that both statically, but also in its dynamic. And that's interesting. When you think of solid ion conducting materials, which are used as electrolytes, then this is more difficult to study with SECM because these are thick layers. So you would have a behavior which is not electron conducting. So you would reconfirm that and then that's it. On the other hand, the ion conduction, to study the ion conduction with the SECM requires a different set of tips and so on. So I think that is more difficult, yeah, because you need to address then the ion conductance thing. Again, you could use this substrate generation tip collection mode, but that would require to miniaturize the surface of your ion conducting material in order to make it at least quantitative.
Yeah.
That's a kind of difficult to work. The SECM needs a liquid phase, otherwise you cannot scan or move the microelectrode. So that's the point. Okay, other questions?
Okay, thank you, Professor.
Thanks, Professor, for a nice talk and answering the comments and queries of our participants. Thanks again, Professor.
Yeah, thank you very much for your attention and for the kind invitation.
Thank you.
Thank you, sir.
And to participants, probably I just want to say one thing. See, we as a society, we are promoting science, and we also will be trying our best to connect ourselves with International Society of Electrochemistry for our next evening lecture series. And so that will be definitely interesting. We'll be inviting further international experts in the related field. And as a membership appeal, please be a member of the society. You can find the website in the invitation brochure itself. And definitely we will promote science in this area. Thank you so much. Thanks, Professor, once again for your time.
Yeah.
Thanks.